Question 84, consider triangle ABC with vertices at 2, 3, 6, 6, and 8, -5. Draw this triangle on graph paper. Is triangle ABC a right triangle? And justify your answer. So I've got this kind of set up already over here. I've got a nice looking little grid, and I've written down the points again. Let's go ahead and plot these. So my first point is over at over 2 and then up 3. And this is point A. So let's label that A. The next point I have is X is 6 and Y is 6. So I went over 6, up 6. And this is point B. And my final point is, it's at -5. So X is +8. So I'm over 5, 6, 7, and 8. It's on this line. And I need to go all the way down to -5. So this point right here is the final point of this triangle, and that's point C. Let me go ahead and draw the lines that connect those. Okay, so there are all of our points, or I'm sorry, our line segments drawn in. So this certainly appears to be a right triangle, and if it were, this angle right here would be my candidate for the right angle. But probably not enough just to say that it looks like a right angle, and maybe even grabbing a protractor and measuring it probably wouldn't be adequate. So let's go ahead and take a look at this. I do know that lines that are perpendicular have to have slopes that are opposite reciprocals on the Cartesian coordinate plane. So I'm going to look at a couple of these. I'm going to look at the slopes of line segment AB and the slope of line segment AC. So if I'm looking at AB, from A to B, I move up 1, 2, 3 units, and then I move over 1, 2, 3, and 4 units. So this line segment AB has a slope of 3/4, and CD, I don't think this is the same, or say I go down 1, 2, 3, 4, 5, 6, 7, and 8, and I went over 1, 2, 4, 5, and 6. Oh, well, actually I just went down 8 and over 6. Which does reduce to -4/3. So this line segment has a slope of -4/3. Well, actually, those are opposite reciprocals of each other. So this really is a right angle. So let's go ahead and write that down in our summary here. I'm going to say the slopes of side AB, or segment AB, and AC are 3/4 and -4/3 respectively. I mean, I wrote them in the same order that they are. Since these are opposites, one's positive, one's negatives. One's positive, one's negative. So they're opposites. And reciprocals. I can conclude, CONCLUDE, that angle A is a right angle. So triangle ABC is a right triangle. That's nice. It's so embarrassing when you get the wrong triangle, but I got the right triangle there. Next it says reflect ABC across AC to create A prime, B prime, C prime. Find the location of B prime. Justify that the resulting figure is an isosceles triangle. Fascinating. So I've got this B, and I'm going to reflect the entire shape. This entire shape is going to get reflected across line segment AC. And I can certainly visualize what's going on here. And, just to take this whole triangle and reflect it across this line, this is going to be my line of reflection. really I just need to move B. And actually, it's going to be on this line, and I've got to go down 1, 2, 3, and then I got to go 1, 2, 3, and 4. I think this is my new point B. In fact, we'll call it B prime. It's where B is moving to. And actually, A prime and A are the same point, and C prime and C are the same point. So the only thing that's really changed is that B prime is in a completely different location. So let's grab this line tool. I'm going to connect this segment there. Beautiful. And, well, actually a little bit off, isn't it? And do the same thing from C all the way back to B. Okay, so here's my new shape, and I'm supposed to verify that this is an isosceles triangle. Well, it looks to me like B prime C prime is congruent to B C prime, right? To me, what looks like is happening is that this side is congruent to this side. So I've got to come up with a convincing. I got to convince us that those two are congruent to each other. Well, they certainly should be because of the reflection, right? But I don't know what I'm talking about. So let's do it by slopes. Well, no, let's do it using the Pythagorean theorem. So if I was going to go from, well, I guess I'll use red. If I was going to go from B down here, that's a 1, 2, and then I would have to go down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So I have this little right triangle I just did that's got a 2 and an 11. And the length of that segment from B to C, right, from B to C, the length of segment BC is equal to 4 plus 121, which looks like, well, the square root of that, which looks like 125. The square root of 125. Actually, that's a nice number, isn't it? It's is it the square root of, is it 15? Yeah, 15? No, it's not 15. No, that's not a perfect square at all. Like 11 is 121. 12 is 144. That's in between them. It's not a perfect square. But it's certainly the square root of 125, and we'll just leave it like that. Let's do the same thing with this other segment, right? From B prime to C prime. That's 1, 2, 3, 4, 5 units long, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 units long. So I think I've got a 10 squared, and what did I say? 1, 2, 3, 4, 5, plus a 5 squared, which is 100, plus 25, which is 125. So the length of the other segment is also 125. So since they're both equal to, the square root of 125 here, and over here we've got the square root of 125, it is very clear that this is an isosceles triangle with BC being congruent to B prime, C prime. So I think I will say by the Pythagorean theorem, BC is congruent to B prime, C prime. Oops, that's supposed to be a C prime. So the triangle, and what triangle am I talking about? The big one, right? Which is B to B prime to C, or C prime, is isosceles. By the way, the definition of that, it has at least 2 congruent sides. I should write that. Has at least 2 congruent sides. And it clearly does. It has 2 congruent sides at least. And I didn't even look at from B to B prime to B. It might be equilateral. I doubt it though. All right, that's it for this question.